All right, it's good. Looks like the audio's working. Good stuff. Since you're the first one in here. What's that?
Right.
Yeah, you get your question answered first. I think that we talked about hydrogenation of aromatics. And it's not platinum. And I remember that because when we went over it the other day, I specifically thought, oh, it's not platinum. I want to say it's nickel. That gets used to hydrogenate those. Let me pull up one of the textbooks.
Yeah, that sounds great. I was wondering more like not necessarily just hydrogenation, just in general, that idea of like kind of like almost like an enzyme does or orients in a certain way.
Oh,
Some way because I feel like benzene is particularly set up for that because it's so planar.
so there are certain aspects that happen. One of the main things that happens is that when you condense aromatic compounds, they tend to stack really neatly on top of each other because of the pi clouds interacting. You get those favorable pi interactions. It's not really a catalyst, but it's part of what makes them good conductors. Is when you get that pi overlap. If you have a couple layers of graphene on top of each other.
That's what graphite is basically. Right?
Graphite is just stacks of graphene, right? And you can the electrons move best along the sheet of graphene, but they can move from sheet to sheet because of that pi overlap. There's just a little bit higher barrier to it. And you do see that's one of the reasons why when we do recrystallizations or especially with sublimation or deposition reactions where you use sublimation to purify these things. I don't think you were in the class, but one of the first labs we did, we used sublimation to purify naphthalene. We had naphthalene with some impurity in it, and we sublimated the naphthalene and then collected it on the bottom of a watch glass that had some ice on top. And it grows in these like needle-like structures. And that's because specifically of the pi clouds. They will grow preferentially in one direction. They'll grow on top of each other rather than growing sideways. So any organic compound, when we do a recrystallization, you tend to see they describe them as needle-like crystals because of that pi overlap. But I can't think of any short of actually going into enzymes. I can't think of any particular reactions that are really specific to the orientation the same way. Then again, that's also a pretty niche topic in research. Then there was I took a whole graduate level class on surface science where we talked about layer deposition and what happens when the reactions only happen on a surface versus happening in 3 dimensions. It turns out you get some interesting properties, and that's part of how you grow like nanocrystals, nanodots, and some of that nanotech structures is by controlling it on the surface level. So on the spot, I'm not coming up with anything specifically, but I'm sure that there's some research being done on that. And actually, if you can, there was one guy who got all of his papers retracted because it turns out he'd been fabricating his data. But the idea of making molecular sized electrical components, like a transistor the size of a single molecule, or a capacitor the size of a single molecule, or just molecular, what do they call them? Molecular machines. You can basically design something that's similar to a car with 4 wheels that basically climbs along pi clouds. And it's basically got buckyballs for wheels. And if you apply a current to it, it drives it across a conductor.
That's wild.
I think that they won a Nobel Prize for that. That one's actually supported, but there's this idea of trying to design things smaller and smaller, and kind of positioning them at the atomic level that's what nanotech really is. nanotech was AI, was like the buzzword when I was in grad school. Nanotech was the big buzzword and nobody knew really what it meant. After nanotech, it was CRISPR, and now it's AI. Nobody really knows what any of these things do unless you work in that field. But Jerry, good catch on the Master Organic Chemistry. Says Friedel traps acylation yields no products with strong deactivating groups. That's one of those things where it's really a spectrum. Yeah, nitro groups are probably the most strongly deactivating groups that we see on a regular basis. And it's just one of those, where do you set the line for calling it no reaction?
So on the quiz, I drew out.
I saw that.
Would be
the
product, but I also said
that's the ideal response on the test too. If I ask you a question like that on test, I'm pretty sure this is a no reaction, but if it did react, here's what it would be. That's perfect.
Okay, cool. I just wanted to.
Yeah, it's the one that gets classically called out for being like, here is this one never reacts. If there's deactivating group is the alkylation, but with a strong enough deactivating group, all of your other reactions are going to slow down. And the next slowest one is the acylation. So Master Organic Chemistry, he has more experience in the lab with this stuff than I do. He says no reaction for acylation. I'm okay with that too. So when you have the strong deactivating groups for acylation, you won't see that reaction either. All right, so quick review. The benzene ring has more than one substituent. The directors will either work with each other, like in the case of our TNT substitution, or they'll oppose each other if we go with the more powerful activating, more powerful electron donating group will determine the substituent placement. So are these are the quiz questions. So with the nitro group, ideally, we could have said no reaction, but if we said, okay, well, it is an acylation. Remember, we lose that chloride on the acyl chloride. So meta director. So we actually get that as our product. If it reacts, this is going to be a slow one. Deact is a weakly deactivating, so still expected to react. And those are the exceptions. Are deactivating but the OP director. Right, so we're expecting ortho and para, so we should get both reactions. So both products, I should say. Then you get the other one. We had enough of the acyl chloride, we'd actually add two to the same, potentially to all of them, but we get the two products here, ortho product and then para product. Strongly deactivating, but strongly activating. So in this case, strongly activating takes precedence, pointed out strongly activating. So in this case, they work together, right? So we're going to see OP director and the meta director, both can be satisfied at the same time.
With the one just approximately OH being strongly favored. Oh no, because they're both going together.
These, the orientation, trying to keep both orientations at the same time, it's easy to do that. In this case, we have two strongly activating groups, and the ortho and para positions are all open. So they're not conflicting with each other. So we actually get three products in this case, because the ortho positions are not symmetrical in this case, right? Okay, the only substituent we wouldn't see is right here. Right, which it begs the question of how the heck do we make this in the first place? If these are both OP directors, how do we put them in the meta position relative to each other? And it turns out that's what we're going to talk about today. There's another class of substitution. We actually can do nucleophilic substitution on a benzene ring with the right substituents. It's a little bit finicky to get it to work. basically you have to have a strongly withdrawn group. In the para position. You do that, it pulls enough electron density away, you can actually do a substitution as long as the group you're trying to substitute is a good leaving group as well. So pretty, like a lot of caveats there, right? But turns out there are some other reactions there. I think everybody got the hang of this one. I will also note, so we do make a weak acid as our product here. And one of you wrote in equilibrium with the deprotonated form, which is true. But remember, we're doing this in fuming sulfuric acid.
Yeah.
So it's gonna stay protonated. That's the
I wrote
really
that down.
weak, that one. Like, as soon as we take it out of the fuming sulfuric acid, you're absolutely right that it's gonna be in equilibrium.
I wrote that down in my first picture I took. And I was like,
And as far as weak acids go, it's a pretty strong weak acid because we do get all this resonance that's happening. It's not as strong as sulfuric acid. But we're really not going to see that until we put it into another system, just because sulfuric acid is about the strongest acid we have, short of hydroiodic acid. I believe it's stronger than hydrobromic, and I know it's stronger than nitric acid. We saw that last week, right? So for the most part, anything in sulfuric acid is going to stay protonated. I mean, just start, because it's probably been a while since you thought about pKa values of these weak acids. pKa value of sulfuric acid, I want to say it's like -19 or something like that. And the pKa value of hydrogen sulfates, the second proton, the pKa is still like 2. It's still
very strong.
Still very strong acid, even the second proton. So it's sort of the gold standard for nothing is really more acidic than sulfuric acid. It's one of the reasons why it's so nasty to work with. Plus, if you do deprotonate it enough, if you have too much sulfate dissolved in your solvent, you'll actually wind up making sulfur trioxide gas as a result. So it's nasty in a number of ways. All right, these are I left this in. I thought I got rid of this one because this is the ones we ended with. This was not on the quiz. If it's tri-substituted, no different than di-substituted, right? If they are all working together like they are in this case, then you can satisfy everything. Meta director, OP director, and there's only the para position open, which is also meta to the other two. So, well, we get the third or the fourth substitution via chloride added right there. One of these I thought was interesting. So OP director and an OP director and an OP director. What do we do with that one? Yeah, oxygen matters more.
To that.
So, which is also going to satisfy this one, right? So we have weakly activating and strongly activating that are working in concert with each other, and then weakly activating that's opposing the other two. Act like that one's not there, basically. The bottom one is tri-substituted and they're all different. So that one's fun to look at. You know, the more we can think about this stuff, the better, right? Oh. Strongly activating, weakly deactivating, strongly deactivating. As soon as you find you're strongly activating, that's all that matters, right? So OP director, the only position open is right here. So we're gonna put a nitrate, another nitro group right here.
Which is also meta to the nitro.
Which is also meta to the nitro group, right? So satisfy 2 out of the 3. All right. So here's our nucleophilic substitution aromatic. So SN-AR. Got SN1, SN2. In fact, during break, I'm gonna find in intro to Gen Chem, when we're first learning how to classify reactions, I basically break it down like there's 1,000,001 different ways to classify reactions. Here's how organic chemists can look at it. It's actually a pretty good little matrix. Things are either nucleophilic, aromatic, or radical reactions. And they can either be substitution, addition, or elimination. And so you can have, any combination of those. But anyway, call it SN-AR, or just aromatic substitution. Like I said, there's a lot of caveats here. You need a strong nucleophile. You need a strong electron withdrawing group, which is usually NO2, which has to be in the ortho or para position to your leaving group. And when I say good leaving group, use our standard definition there, halogen. Anytime we're talking about a good leaving group, that's usually what we're talking about. And if in this case, basically what we wind up doing is our strong nucleophile just replaces the bromine. So really very similar to what we've seen before. It's almost like a mashup of just SN2, but also the electrophilic aromatic substitution, because it does have an intermediate with a whole bunch of resonance, just like electrophilic substitution. So first step is your nucleophile attacks. And it's going to attack where your leaving group is attached, because due to the resonance and the electron withdrawing nature here, that's the carbon, those carbons in the ortho and para position are the ones that actually have a slight partial positive, or at least the least negative out of all of the carbons in the benzene ring. Plus, as long as your leaving group is in the ortho or para position, once your nucleophile attacks and you make an SN3 carbon sp3 carbon temporarily, we wind up with something really similar to a sigma complex. It's called a Meisenheimer complex instead of a sigma complex, because it's a negative charge resonating around instead of a positive charge. But it looks really similar, right? We break pi bond, one of the 3 pi bonds here, and then we can resonate that charge around. And then having the nitro group or strong electron withdrawing group there means we can resonate some of that charge into your electron withdrawn. And then just like before, we kick one of these 2 groups off to restore the aromaticity. Right, so it's not a reduction or an oxidation. We still keep our aromatic character. It's really the fact that it's a separate mechanism than SN2 because it's not concerted. And it's not SN1 because the first step is your nucleophile attacks. Remember, SN1, the first step was leaving group leaves. So it really is its own thing, but it's definitely a nucleophile and it's definitely substitution. So we get a new classification for it. Simple enough, right? The big trick is remembering all those caveats. Where again, strong electron withdrawing group in the ortho pair position, and you have to have a good leaving group, meaning a halogen for the most part. So here's a good example. Strong electron withdrawing group, strong nucleophile and heat. What's our product going to be? Well, it's not gonna be an alcohol. It's not gonna be an alcohol because our nucleophile is a methoxy. So we're gonna add a methoxy group where the chlorine is, and the bromine stays untouched. The second one, I'm thinking it's either kind of a deep pull review, or we may not have covered it. And did we talk about reducing nitro groups? I don't think we did either. So nitro groups can be reduced by using super strong reducing agent. What's our strongest possible reducing agent that we've used for carboxylic acids? Lithium aluminum hydride. If you put a nitro group with lithium aluminum hydride, you get the amine. You basically remove all the oxygens and turn it into an amine group. So with that in mind,
So it's a nitro group too.
we don't have another way of adding a nitrogen to anything other than a nitro group at this, I guess, to anything aromatic. But if you know you can turn a nitro group into an amine, then the trick is just figuring out the right steps in the right order to get things placed properly. So take a few seconds. I'm going to see if I can find that reaction since I have the textbook up. I take it back. So it was in the benzene section, we just skipped over it in one of the things is like, if you make a nitro, if you add nitro group, here's the next thing you can do with it. But it's not lithium aluminum hydride. If you just hydrogenate a nitro group, you get an amine out of it.
Oh,
Or-
it's just hydrogenating it with the
Yeah.
catalyst.
Yeah, or you can reduce it with a metal. So it doesn't even need to be a strong reducing agent, you don't even need a hydride source, you put it with a metal, nitro groups are reactive enough. That if you put it with just zinc shavings. Added to a nitro group, you get the amine out of it. Right, so we have a couple options there. Hydrogenation makes the most sense. Maybe not if you're in the lab, because then you have to deal with hydrogen gas and platinum catalyst, but as far as on paper, that's pretty simple. So what order do we want to go in for these? For these steps, we're starting from benzene. We have, go ahead.
I was thinking of maybe putting on the halide first. Because it still acts as like an ortho para director.
Bingo. So if we put the halogen on first, so we kind of know that we're gonna go through. Since we only have one reaction to turn the nitro into an amine, we have one reaction to turn a halide into a an OH group. Then that means we're gonna go through an intermediate that looks like this. With the nitro group on one side and just make it bromine for the ease. Since bromine's such a good leaving group. So now if we can get here, we can get to our final product. So the question is, how do we get from benzene to here? And if we put the nitro group on first, we can't put the bromine in the para position.
Because it'll always want to go meta.
It'll want to go meta. So we start by brominating. So Br2 and iron. And then Verona solution. And it's not gonna be great yield. So H2SO4.
So
HNO3,
you're gonna get the mixture.
because you're gonna get the ortho para
Yeah.
mixture, and which is gonna favor the para, or sorry, it's gonna favor the ortho because there's two of those carbons.
Mhm.
So we're right off the bat limiting ourselves like a 30% yield, even without all the other reactions. But that will give us our intermediate here, redrawing it when it's right next to us. Then once we have the bromine and the nitro group on there, the nitro group's more reactive, so we'll probably react that first, turn it to the amine first. And then oh no, we can't.
No, we cannot because it has to be strong.
You guys need the strongly deactivating group, so next order or next reaction has to be NaOH 70 Celsius. And that gives us the nitrophenol. Then we can do H2 over platinum or iron shavings.
Does that sodium? Does that step need to be in acidic solution?
The step, well, if it's hydroxide, it can't be. We need a strong nucleophile, which is gonna be basic conditions.
And I also saw with the other method of doing it with the like zinc shavings, you also add in the NaOH as well along with it.
Yeah, and
Is
that's
that
mainly
required?
just to deprotonate, because So let's talk that one through.
The very first slide when we started covering this, so it's in.
Because that's the second step.
Anyways, the second step, this has to be acidic. So there's gonna be a lot to go through this whole process, there's gonna be a lot of neutralize, purify, extract, redo it. Because we're switching back and forth all the time. So the first step here, we need to be acidic so that we have a source of hydrogens. Otherwise, we don't have any hydrogens to put onto our nitrogen here. What will happen is we'll reduce the nitrogen, but then you need to add, then you add nitrogen with a negative charge, so you add deprotonate.
Yeah.
Then the second step though is when you make the amine group in an acidic solution, amines are a pretty good basis. So if you want the neutral product at the end instead of the quaternary amine, then you've got to you have to deprotonate it, put it in the acidic solution. So it's not as critical, but we would actually wind up with it being protonated, which is not the end of the world. It's just a quick acid base reaction away from being deprotonated. But depending on how we're trying to extract it and purify it at the end, probably want it neutral. So they just say neutralize. And so lots of things to keep in mind with these. Got, for the most part, it's ortho versus para, and doing that in the right order winds up being the most significant thing to keep in mind when we're trying to do synthesis on a benzene ring. But once you have that planned out, it actually kind of, working backwards, you can say, okay, well, if I need it to be ortho para and these are my two groups I'm trying to add, it's not too bad as long as we can remember anything with a lone pair is ortho para director, anything with a double bond conjugated is going to be a meta director. And this gives us a way, that last reaction we just added gives us a way to turn a meta director into an OP director as well. So we have that as an option as well. We don't have another way of adding an OH group. If you think back to all of our electrophilic aromatic substitutions, we don't have an OH group. What we do have is halogens and then nucleophilic substitution. This one's a funky mechanism. So this one's called elimination addition. It's exactly what it sounds like. What do you get when you do an elimination? You follow it up with an addition. The substitution.
Substitution, yeah.
But it works in a very weird way. And you'll notice this is also not a particularly fun reaction to do in a lab, because sodium hydroxide at 350 Celsius.
That's fun.
Yeah, it's not ideal. If we do it, if we heat it hard enough with a strong enough base, we can get this to happen without an electron withdrawal group. And we know that this is going to be weird because when we do this on a substituted benzene, when we do this on toluene, we actually wind up with, so this is used with another strong base. Technically, you do this with any strong base. So if we do that with amide, and they're just using liquid ammonia as the solvent, since we're using amide as the base. We don't get ortho para versus meta, we get the para and the meta. So that's your first hint that something weird is going on, right? It doesn't match with any, so it's not going to go through one of those sigma complexes, Mesenheimer complexes. So something else is happening here.
Would the chlorine So I'm just kind of confused why on the left, there's no reaction. With just an NaOH and heat, on the right, the NaOH and heat, is it the second step of the acidic solution, or what's the?
It's the extent of the heat. Heat usually means like 70 to 100 Celsius. 70 Celsius gets used a lot because that's close to the boiling point of benzene, if I remember properly. So if we're using benzene as our solvent, we're kind of limited there, unless we do something like put it under pressure or switch your solvent. You can just do this reaction at pressure to raise your boiling point, effectively making a pressure cooker. But again, pressure cookers are a metaphor for an unstable situation for a reason. So what we wind up seeing, what they did to figure this out is they made benzene or made chlorobenzene with one of your chlorines as the carbon 14. If it's carbon 14, we can tell which carbon is which. What they saw is that they only added, you had a 50-50 mixture of adding your base, your nucleophile to the same carbon where the chlorine was attached and the adjacent carbon where the chlorine was attached. And it was a 50-50 mixture. And so what they postulated, that the current understanding, current hypothesis, is that it actually makes benzyne.
Sure.
Current understanding.
Current understanding. It
That's
looks,
wild.
yeah.
Looks wild.
So basically, it's called elimination addition, right? So you go through an elimination reaction first. If you have a strong enough base at a high enough temperature, you can force it to go through an elimination.
Which is why you need that insanely high temperature.
Which is why you need that insanely high temperature. So when you do that, you wind up with the extra pair of electrons after your base pulls off the hydrogen. So similar to a lot of elimination mechanisms we've seen. And then your leaving group leaves. And in doing so, if you just had your leaving group leaves, we'd be left with a positive charge next to a negative charge. That's not very stable. So you actually wind up making another pi bond that's not part of the aromatic system, which means it'll just behave basically like an isolated alkene. Even though it's a triple bond, let's just say that the extra bond is the one drawn on the outside. These three are part of the pi system. That one's not.
That one's just chilling there.
That one's just chilling there. And now we can just do a regular addition reaction.
So what would the geometry be like on?
Really strained.
Yeah.
Really strange.
Because you're gonna wind up, like, think about the shape of a pi bond has that above and below, right? In this case, if your pi cloud for the benzene ring is above and below as a donut shape,
Would it just be stacked on top?
it would be inside the donut and outside of the ring. So we've got our sigma bond, we've got our pi system here. And our pi system, the other phase of it down here, that's looking like a donut. That's just, I'm just drawing it from the end on. This one is gonna be here. And behind it on the inside of the ring. Like in between the top donut and the bottom donut is gonna be one of the lobes of your second bond. So it's got, and it's, you know, this is sp carbon now, but it's forced to be, instead of, it wants to be at 180 and it's forced to be at what, 120? So it's bent 60 degrees out of its ideal geometry. So there's a lot of strain energy and there's a lot of electron crowding in here because you've got those other sigma bonds that are this way into the board, the other part of the benzene ring, are basically squishing this other pi bond. The inside shaded part of the pi bond is getting crushed from the side. So if we took this and flipped it over, we've got our pi bonds, our cloud, the aromatic cloud is the donut above and below. We basically have
Oh, okay, that makes.
This is technically not an aromatic.
it still is aromatic because the red bond is separate from the rest of it.
Right.
So the blue pi bonds are all still resonating, they're all still aromatic. And so this is almost like behaving like a lone pair. The way that we can have a lone pair that's not part of the benzene ring, except because it's actually a pi bond, part of it is not just sticking out away 90 or 180 degrees from everything else. Part of it is stuck inside. I don't think I have a good. We're gonna take a break here in a minute. I'll see if I can find a good picture of the orbitals of benzene. Because somebody's calculated this at some point. And it has good figures for it. But basically, the whole point is that now we've got a pi bond that's not part of the aromatic system. So it should react like a regular pi bond, if anything, more reactive because it's squished. Right, the overall step is proton transfer to make a negative charge, basically give a carbon with a lone pair. And then if you have a good leaving group, your leaving group can leave and you make that benzene. And then it just acts like a nucleophilic addition. So nucleophile attacks one of the two carbons from the benzene, from the alkyne part. And then you go back to having a negative charge, which then just grabs another hydrogen from something around. Amazing how many different mechanisms, how widely varied they can be, considering we're still mostly just working with our same 4 mechanism steps that we learned back in October. And it's still all nucleophile attack, loss of the leaving group, proton transfer, and maybe a rearrangement here or there. We had a couple of new wrinkles like aromaticity, and all of a sudden we have 15 new mechanisms that look a little bit different. And so last step before we take our break, and we'll recap this again in a second, is obviously benzene is going to be pretty unstable, but we can show that it does react because we can actually get benzene to go through a Diels-Alder reaction. If you put benzene with a diene, you can actually have it act as a dienophile. We can make this product and get an observable.
Just because that pi cloud, you can use it,
Exactly.
but it will still keep the aromaticity.
It'll still keep the aromaticity on this part that looks all skewed because it's really hard to draw these shapes in 2 dimensions. But yeah, we can actually get it. So it seemed like that was a big leap, but all of a sudden, like, well, that actually seems kind of reasonable now. And I'm not promising that this will be on midterm, but I do like to make you draw funky stuff like this sometimes on a test, right? So benzene plus a diene might show up. All right, so when you get that one drawn, let's take our break. And let's come back We'll round up. We'll come back at 11. And we're just gonna practice with these couple mechanisms and reactions. Search engines. Type in benzene orbitals. Did you mean benzene orbitals?
For certain things. Yeah, well, I don't think about like customization stuff, random, rigor.
made it in there.
That's amazing. I love that.
And they just, like, all the security dudes and people working in there, just. Oh, fuck. What the hell, like, they weren't even like, mad, they were just.
Stress. It's not like you did it on purpose, did you?
I don't think so. Yeah.
That's what it does.
That's what does.
I'll be right back. We'll get some pressure.
Super cold. Still got a half a fucking slide deck here.
Did you go to any, 420 or something?
No,
No.
that's stayed at home. Talked to Kyle for a little bit. Started smoking yet.
Hey, you gonna be.
He was all trying to smoke a Camel, fucking started, he wanted to smoke a cigarette, he said he hasn't smoked a cigarette in like 2 months, so.
Did you smoke a can?
No, he didn't, he just like, he pulled that out of the pack and I saw him do it over the video camera, I was like, yeah. Snap it at him.
Keeping good restraint on the sins.
I've been smoking them.
But you know, it's not
Right.
hard. Got no fucking Marvel Reds.
Any like your reds?
I like my Reds, you know, too many of them on there, but they have the Southern cuts.
Oh, okay.
Those ones are good.
Have you tried the 77s?
Heck, no.
Those are fucking really good, they're really tasty, but they're expensive.
Yeah, I heard. And then, I don't know, like, I used to be, when I was in high school, I was like, I thought it was really cool. No filter fucking Turkish. What's it with you walking around being disgusting?
I was smoking the Turkish Royals in high school. Yeah, I liked those. They were just so thick, they're like a cigar, so you don't smoke them forever. But I like American Spirits now.
American Spirits, that's your.
Yeah. The grape series was. I used to like the filterless naturals. Those were
Oh,
pretty good.
yeah.
Smoke it down where it's just like nothing. It just smokes into nothing. Oh. Yeah,
Well, at least, oh,
he appreciates being better of this chat about that. It means more reason not to do it, you know?
yeah. I'm just, I think it's because roommate situations, so.
Well, I don't think that's, yeah, I don't think that's really affecting cigarette smoking. Or sleep, yeah. It's more just like day to day, like, just annoyed by them not taking out the trash, like, okay.
Did you apply for high school?
No, I haven't applied for it. No. I don't know. I'm gonna start tomorrow, this is like, it's actually. Now,
The foreign language?
no.
So
People.
For transfer, for transfers, do not.
for transfers in the STEM degree, you don't need everything on the GE pattern.
Yeah.
You can pick like 1 or 2 classes and say, because STEM majors have so many units in lower division units that you have to take while you're here. They make an exception for STEM majors that are transferring to UCs. Where you can, I think it's either 1 or 2 classes. You can basically say, I'm gonna take it when I get there. You still have to take it, but you can do it after you transfer.
Then when I went in high school, I also did the Spanish, like other language requirements, so they probably will just.
Yeah, I did Spanish.
Which was one of the few classes I actually like tried. In high school.
I had one of the teachers from the high school that got suspended for pulling a knife off student. This is what it was.
Wait, who was it?
Mr. Wright.
Oh, Mr. Wright, oh, I remember that story, oh, that dude.
All right. I did find a couple of good figures about what these orbitals look like. So just to have an idea. So this is from our textbook. From the Ocean Stacks textbook. If you look at the electron density, it doesn't show the orbitals quite as well, but you can definitely see how you get like extra electron density over here where you're missing the hydrogens. And then here's kind of what I was trying to draw here. If you picture these ones that are blue and red, those are the donut of the pi electrons. But then these ones that are green are going to overlap to form that other pi bond, and the other side of them, the shaded, the other phase, is stuck in the middle of this. It is stuck right here in between the two donuts of the aromaticity. And so nobody has one that's exactly what I was looking for. What is the command? Is it? I don't remember the keyboard shortcut. Let's guess a quick into the right spot. And this one's still not entirely accurate because it says sp2 orbital. Technically, these carbons are going to be sp,
Right, yeah.
because these other unhybridized orbitals are going to be part of the pi structure. So this is why it basically will act just like a regular alkene, because all those aromatic electrons are essentially stuck away from the rest of the pi bond. And so this pi bond is perpendicular to the pi cloud for the benzene. All right, so let's do some practice with these. We've got a whole bunch of aromatic reactions now. We've got 4-chloro-2-methyl-toluene is treated with sodium amide and high temperatures. Yeah. So it's
There's
gonna
also another one.
and there's another one.
That's.
Right. In the class, the old school common name for 2-methyl-toluene would be orthoxylene. Xylene.
Oh, the
is
xylene
common
thing you have.
dimethylbenzene, yeah. So orthoxylene for 2-methyl-toluene or 1,2-dimethylbenzene. Both products, but I think we're actually going to see. No. Two of them are going to be the same. So we're going to get two different benzynes. It's one of those things where it's almost impossible to do it in your head. So we're going to get a benzyne there. We're going to also get a benzyne here. Those are really this. Are those going to be the same? those are gonna be different, right? Because we've got the benzyne, one carbon away from a methyl, or benzyne ops meta to both methyls. So then when we follow that up. Yeah, okay. With our nucleophilic attack, it can attack any of these 3 carbons. But those 2 are gonna be identical. So we're gonna get one product where. Where our amine is meta to one methyl and para to the other. If we put it here, it's also meta to one methyl and para to the other. So then the other product we could get. Like that. And since it is followed up with treatment with H3O plus, it actually wouldn't be incorrect to put NH3 with a positive charge on both of these, the protonated amine salt. But I wouldn't mark either of them down. Since we don't usually draw our final products as charged. By the way, we could tell the difference between the 2, putting the nitrogen here and here, is if we did one of those isotopic substitutions. If one of these was a carbon 14, then we'd be able to tell the difference between them. But as it is, they're the same. Ratio of carbon 14 to carbon 12 under natural conditions, even coming from fossil fuels, especially, it's going to be effectively 0. There's no, the only source of carbon 14 in the natural world on Earth is what we get from atmospheric CO2. That gets, which is really nitrogen that gets hit with high energy light from the sun in the upper atmosphere. So you do get some carbon 14 occurring naturally. That's how we do carbon 14 dating, right? Bit of a recap back from Gen Chem. Anybody remember what the half-life is though on carbon 14?
It's like 2,000?
5,000.
5,000.
I think I'm gonna go off of I think it's 5,730 years. Only hold me to 2 things on them. Which means if we're getting our benzene from fossil fuels, there's 0 carbon 14 in it because it's been so many millions of years that there's effectively nothing left of it. Which that's the other thing I like to point out where, like, Jerry, you had me for Gen Chem 3, right?
Yeah.
When we talked about nuclear chemistry. What you're really dating when you are using carbon 14 dating is you're dating when that material stops taking in atmospheric CO2, which means you can only use it for things that either photosynthesize or things that eat things that photosynthesize. And basically you're dating the date of death of that organism when it stopped intaking food in the form of CO2 or in the form of sugar from.
So you can't just do it with random, like a
Right.
rock.
You can't use carbon 14 dating on a rock because there is no carbon 14 in the rock. Even if it would naturally have carbon in that rock, like something like, well, coal's a bad example because it's a fossil fuel again, but like a diamond, say.
Yeah, diamond.
It's still is going to have 0 carbon 14 in it, even if it's freshly made. diamond because it wasn't photosynthesizing atmospheric CO2. And so carbon-14 gets used a lot for labeling. Plus, it is radioactive, which is actually a benefit when you're doing biochem studies. Because that means you can track where it is in the cell just by looking for radiation. You can use basically a Geiger counter microscope to figure out where the carbon-14 is in the cell. If you only need to narrow it down to a specific organelle, it's a pretty easy way to do that, do radioactive labeling. If you need the actual structure of it, then it gets a little bit trickier. But we can still use, what do they use? It's not, I think a proton NMR will show up differently if it's a hydrogen that's attached to carbon-14 compared to a carbon-12. You get splitting occurs differently. So I think you can use a proton NMR to tell where the carbon-14 is in the structure. But now I'm second guessing myself. So definitely don't quote me on 5,730. What do you quote me on that? All right, let's do another quick synthesis problem. Trying to make anisole, methoxybenzene. How are we gonna do that? Starting just from benzene. Just brominate it. As long as we brominate it, so iron and bromine gives us bromobenzene. Then we use our sodium methoxide and heat. Get a benzene intermediate. We don't need to worry about the substitution in this case, or about where, what isomer we're getting. But if it is a substituted disubstituted product we're trying to make, we might have to be careful about what order we do things in. This is an OP director, and so is this. This is strongly activating though. So if we want that to be the case, that's pretty easy to do. If we want our product to be meta, we would have to add our other substituent first, like we talked about before. Depends on how strong the base is, but yeah, that's a good ballpark. I think with sodium amide, because amide is so much stronger of a base, you can get away with it being a little bit lower, but you're working with a nastier reagent. But I think for all of the deprotonated alcohols, it's going to be around 350 because they're all about the same pKa. So here's a recap. Let me fix the figure real quick. We've got electrophilic aromatic substitution. That's what we spent the most time on. Goes through the sigma complex, which has a positive charge. And then we kick off a hydrogen. We want to do nucleophilic aromatic substitution. Similar, but it's the Meisenheimer complex with the negative charge. And that's all of our resonance going around here. And then last but not least, we have elimination addition. Right, still need a good leaving group, and you need really high temperatures. And because it goes through that benzene intermediate, that's going to affect what products we get in terms of substitution. The benzene intermediates are always going to be, or the products are always going to be right around where that benzene bond was formed. Right, so no rearrangements really happening here because of the aromaticity.
That last example that we had, would it be elimination addition or nucleophilic substitution? That last example.
Did I say elimination addition or did I say nucleophilic aromatic?
You said elimination.
It would have been elimination addition, because the nucleophilic aromatic has to have that nitro group in the para position. So I misspoke, sorry. Thank you. All right, so if we're trying to predict these, we could just memorize them, but then that falls down if I just switch out what the nucleophile is, right? So it's more about classifying. It's always going to be a benzene if we do these three. If we're going to do a substitution on a benzene, we have to look at, are we going electrophilic or nucleophilic? If it's acidic conditions, that's going to be electrophilic. Right, because all of our strong nucleophiles have to be under basic conditions. So halogens, Piranha solution, fuming sulfuric acid, frigographes are all going to go electrophilic. And they're all going to kick off a hydrogen. Both of these nucleophilic reactions are going to kick off a halogen. And if it's going to be a nucleophilic aromatic substitution, we also need that withdrawing group in the para position. And then if we have strong nucleophiles and a good leaving group, but we don't have an electron withdrawing group, is if we heat it up enough, we can get elimination addition. Just 2 slides of practice problems left. So I'm going to give you plenty of time to go through them, work together.
I'm just finishing up the. I'm just finishing up seeing it, but. I'm dead. No. I can take my time. I can also. Yeah.
That's really the key with the mechanisms. That and remembering if you can identify the mechanism, and then if you know one of the landmark intermediates. That usually helps a lot. I'm gonna get rid of the second set of reactions here. We'll go over those in a second, just so we can focus on these. This first one, substitution with a leaving group and an electrophile. So, but it doesn't have the nitro group. So it's gonna go elimination addition. So the first step is drawing the elimination reaction. So whatever our nucleophile is also gonna act as our base. Most of our strongest nucleophiles are also strong bases. And it really, the first step is, it doesn't happen simultaneously. It's not an E2 reaction where everything's happening simultaneously. We are going to make that intermediate with a negative charge, which then moves over as the bromine takes the electrons with it. That's going to make our benzyne. And really, this step, once you make the benzyne, both of these carbons are equally valid as the target. Which obviously we can't tell the difference between them here, but if we did have another substitution, you could draw it either way. If you're trying to draw one specific isomer, that we're trying to favor, because I told you specifically you're looking for the para isomer versus the meta isomer, then you just pick the right carbon based on where you're trying to put your hydroxide at the end. So now we're back to having a negative charge. We just protonate it. But definitely, and again, a lot of these mechanisms are, they're sort of like the first time you see a new algebra derivation. Like, oh, I never would have thought to do that, but now that I've seen that, that makes a lot of sense. Right, so that's why so much of it is the volume and seeing the tricks and how they get combined in new ways is a big chunk of this part of the series. Give ourselves enough room here, crop out the stuff we're not doing for this part. So this one looks a little bit weird because, oh, I didn't skip to the next slide. This one looks a little bit weird because it's naphthalene, not benzene. It's still just an aromatic, right? The only real wrinkle with naphthalene versus benzene is the fact that now we have two different hydrogens that we could replace. So probably actually get two products when we do this. We get the bromine put in this position versus the bromine put in that position. We won't see any with the bromine in this position though. Right, no hydrogens there. But, and then these two are symmetrical, and these two are symmetrical, and these two are same as over there. So there's only two out of all of the eight hydrogens there. There's only two products we can make. I was thinking about this while you were working on this. I'm not actually sure if it would favor one isomer over the other. My instinct is that they're all pretty much identical in terms of their aromaticity. But I want to see experimental data before I commit to that.
Maybe sterics.
Maybe sterics. There might be something going on. There's not a whole lot, because you do have to make the sigma complex, but both sigma complexes should be pretty much identical. They're both gonna have the same number of resonance structures. But let's draw it out, see what we see. So first step is going to be make the electrophile. So wind up with that little pair goes there. So we make the intermediate, looks like this. Then wind up these electrons. Nope, wrong direction, didn't I? Easy to do. So remember that the sigma complex is positively charged. Make sure that you do that the right way. So then our sigma complex is going to look like bromine here, positive charge there. We're going to have extra sigma complex resonance structures though, right? Because we can put the positive charge here, here, or here, or here. So we'll get a total of, basically for every pi bond you had in the aromatic structure, you'll get one resonance structure in the sigma complex. Unless you've got an electron withdrawing group, which gives you a couple extra sometimes. But if we look at where we can put that positive charge, here it's going to be pretty symmetrical, regardless of where we attach our bromine to begin with. We attach it there versus there, we're going to get the same number of resonance structures, and with the same positive charge in the same spots. So my instinct is that you should get about a 50-50 mixture of the two isomers. And then once we get that, the sigma complex, then we just have to have a base. So we'll just do a bromide. So bromine is attached to the FePr3. And then come in here, grab hydrogen, those electrons go back. And get our peroxide. And so when it's not a substituted aromatic, you don't need to worry about where you're putting the positive charges, then drawing the sigma complex out is a little unnecessary. It's still a good habit to be in. Especially if you blanked on the test and you need to remind yourself, is electron withdrawing mean meta complex or meta director or the para director? If you need to remind yourself of that, the way you do it is with the sigma complex. That's not the most efficient use of your time if you're in a time pressure test though. So that's one of the cases where you can prove it to yourself every time and make it make sense. But on a test, I'd recommend having that memorized. All right. Questions on this one? We beat this mechanism to death, I think. So this one shouldn't be too tricky.
Two options for the same mechanism.
True. All right, so last one. Electron withdrawing group in the para position. Substitution nucleophilic aromatic. So in this case, our strong base just starts by adding. We move the electrons over and we make that Meisenheimer complex, which looks like the sigma complex with a negative charge. That has all resonance structures, but then it's always going to end with we kick off leaving group leaves, so we reform the aromaticity. So consider we started with a synthesis problem where you had to take the nitro group and then turn it into an amine. We now actually have another option as well. We do actually have a way to add a nitrogen directly without it being a nitro group. So we have two routes we could have used now to solve that problem that we started with at the beginning. All right, mechanism questions?
Here.
And the one thing I will say, I know I glossed over the Meisenheimer complex and the sigma complex for these examples in the interest of time. On the midterm, one of your mechanism questions will be one of those two. And I'll specifically say, draw out the Meisenheimer complex or draw out the sigma complex, because that's part of testing you on this. It's showing you can draw the resonance structures. But it'll be one of those two, since they're pretty much analogous. And so the only trick really is just make sure you draw your arrows going the right way. All right, last one. This one's got a little bit of review in it. Some other reactions. So step one here is to add a nitro group. Where are we going to add it? Ortho to the methyl. Then we follow that up with zinc under acidic conditions. Which does what?
Changes the
To the amine. And then step 3 is part of step 2, right? That's just deprotonate the amine. Yeah. B is a friedel-Crafts acylation, and then followed up with another reduction, right? But in this case, the reduction is going to reduce the acyl group in hydrogenate. And so we're gonna start by adding 1, 2, 3, 4 carbons as an acyl group. And these 4 are all identical to each other, right? So it doesn't matter where we draw it. Methyl, methyl, 1, 2, 3, 4, an acyl group. Step 2. Just does that. And it's more than just the straight reduction. It's not just the hydride reductions. We're not turning it to an alcohol. It actually fully removes the oxygen. If we just wanted to stop it at the alcohol, we could use sodium borohydride or lithium aluminum hydride to reduce the oxygen but not remove it. Got going on here. Step 1 is going to add a methyl group, right? And then, yeah, KMNO4 is a fairly strong oxidizer. What is the oxide? We used, I think we saw chromate as an oxidizing agent on benzenes. You needed. So we can also use KMNO4, exactly. So our intermediate is going to look like. Well, we're going to get this is ortho-para director, so we're going to get 2 products. And then the same, except para. Then KMNO4, water and heat, is going to oxidize those benzoic carbons. So we're going to get phthalic acid. We're going to get the dibenzoic acid. Plus the para version. Assuming, of course, stoichiometrically we have enough permanganate for that to work. If you saw it with chromate or chromic acid, be thinking the same thing.
If you put it on exam, like what you just said, compare position type of thing, would you accept that and then true that, you know, said fair position as well?
Yeah.
There will also be 2 methanoic acids floating around.
And there would be 2.
Or what would that be? Or
Those they might just wind up getting fully oxidized to CO2. Because this is the carbon that we're turning the acid we have. Yeah, these 2 methyls, 1 methyl by itself. Formic acid's not all that stable on its own. If we still have some oxidizing agent floating around, it's likely you'll get at least trace amounts of the methanoic acid, but probably CO2. And then last but not least, another Friedel-Crafts calculation followed by NBS. So the Friedel-Crafts calculation is going to give us. So ortho-para director, so again, 2 isomers. What is excess NBS going to do?
Benzoic bromination.
Benzoic bromination. but only where you have hydrogens to replace.
Yeah.
So the T-butyl group is gonna get left alone. And the fact that it says excess means we're gonna do it 3 times. We're gonna replace all of the hydrogens on this benzoic carbon. Here too.
First time I've ever seen that.
It's a lot of bromines. And then we get the same thing over here. And so, and this is when we first learned or reviewed doing the NBS on benzoic carbons. Like, well, seems like we can't really break up the aromaticity, so it seems like we could just use BR2. Which is still kind of true, as long as we make sure we don't have any Lewis acids around. If we have any Lewis acids around, then we get the bromination of the, where we do the electrophilic aromatic substitution. So NBS is still really commonly used, partly just because it's easier to work with. It's a solid, you measure out the mass really easily, it doesn't smell as bad as using liquid bromine. And it's safer to use when you're trying to do something like this, where you want to make sure you don't add a bromine here, for instance. All right, questions on these ones? It's a lot of material, but more of the same, right? I have your lab procedures. So we're going to use our Grignard reagent. We're going to make benzoic acid. We have bromobenzene Grignard reagents. We just expose that to CO2. We can actually use it to reduce the CO2. So we're going to just mix your Grignard reagent with dry ice. And we should get benzoic acid out of it, which crystallizes really cleanly, has a nice, neat melting point. So not a super exotic substance that we're going to make with our Grignard reagent, but one we should prove that we actually made the Grignard reagent we said we did. All right, so I'll see y'all in about an hour. In the meantime, there's free ice cream, I believe, or maybe for a donation. I don't remember the exact situation. Some sort of allyship April event that has ice cream. So if you were wondering to yourself, what am I going to do for lunch? I think you have your answer. Ice cream for lunch.